So let's start this k nearest neighbor algorithm. So next algorithm that we have in our list. So you see what is this? Again, this is a classification algorithm. Okay. So it classifies new data or case based on similarity measure. Classifies a data point based on how its neighbors are classified. So it's very interesting. Why? Because, like for example, sometimes it happens with you as well. Like you are trying to decide. I mean, you should go for a movie or you should go for some other place, and you are actually looking with your friends, and you can see that your friends is divided into two part, and you have decided that okay, let's do one thing. I mean, most of the friends will go in. You will go in that particular site where most of the friends will go. Will decide. So a similar situation like this. So we have a point to classify either 1 or 0, whatever. So we will look some other points around that point, and we will see what is their class level. If majority class level is say towards 1, I will classify with 1. If majority is 0, I will classify 0, something like that. So the idea of classification is entirely different that already you have seen in logistic regression, right? But there is definitely question comes that the point that I've written here, that k is based on similarity measure. So what is similarity? How the similarity is measured? The similarity in the sense, just assume a situation that you have a two features in your data set. If x2 and x1, I mean x1 and x2, okay. And you see, if you imagine that you have a three features in your data set, and three features on in three different axes, x, y, and z, okay. So that means you can place any data point having those three feature within this space as a point, right? And their value will be, say for example, 2 1 3. What does it mean? Means x1 x equal to 2, sorry, x1 equal to 2, x2 equal to 3, x3 equal to 4. I mean, sorry, x1 equal to 2, x2 equal to 1, and x3 equal to 3. 2 1 3, right? And what is this x1 x2 x3? These are three dimensions, because your data set has three components. Any data point is presented by three components, x1 x2 x3. So just try to imagine from a geometry point of view that you have a three-dimensional space where the data points are, say floating on air. Now the location of the point is presented by x1 x2 and x3, which is definitely started from origin. So you can assume like a vector, right? Assume like a vector started from origin, right? So that means, like, the data point that you are looking, other data points are also floating in the same dimension, same space, floating in the air, and there is a difference between these 2 points. Definitely some straight line difference is there. So this straight line difference actually can be considered as how similar these 2 points are. It can be thought as much similar the points are, they will be much closer to each other. So they will be much closer to each other means their distance, the straight line distance will be very less. So that means we have to calculate this distance, and that's why I have written this, how to calculate the distance. There are three different ways actually you can calculate. One we call Euclidean distance, then Manhattan distance, and Minkowski distance. So, it's not like you can say this distance is better than that one, not like that. There are three different people. They have actually, there are many other actually distance metrics possible, but mostly people use one of these three. So it's not like, Euclidean is always better than Manhattan, Manhattan is better than Euclidean. You cannot say like this, you cannot comment like this, but you can check with any of these three and you will get, most probably will get the best result in one of these three if you calculate the distance in this way. So the thing is something like this: you have these points and you have some points here, and you want to find out some unknown point to classify, pointed by red. So what basically we will do, we will first check that, among its neighbor, how much are from green and how much from from say uh, the yellow color, not yellow exactly, whatever, some color, some cream color, some light green or something like that. Based on that, now question is that how I am deciding how many neighbors I will have. That's the question, and that is a part of learning actually, because that implies that, for example, if you keep this one as your neighbor, naturally you will have lot of green points and very less this point, right? And if you have something like this, so you will have lot of these points and very less green points. So which is the best representation, that we have to decide, and that is a part of learning in K nearest neighbor algorithm. So what is the logic actually? The logic, or you can say the algorithm flowchart, looks something like this. What we do, we actually select with an arbitrary k. I mean, k is the number of neighbor. Remember, k nearest neighbor means k is the number of neighbor. And why it is saying nearest neighbor? Because we are applying the classification prediction based on the nearest neighbor of my new point. Now, what is the area under which I will consider nearest neighbor? That is a part of learning. So, anyway, let's see. So, in the step 1, we select with an arbitrary number of k. Okay. We definitely calculate the Euclidean distance of the k number of neighbors. Okay. And take the k nearest neighbor as per the calculated Euclidean distance, or maybe Manhattan distance. Next, among these k neighbors, we count the number of the data points in each category. Okay, what I just told you, and assign the new data point to that category for which the number of neighbor is maximum. Okay, so, and in this way it will move on, and then your model will be ready. So actually we have discussed the k nearest neighbor algorithm in a very nutshell, because if I try to go for the derivation of the error and all, it will take a lot of time. So I'm not going in detail of that, because lot of deep mathematics of k nearest neighbor might not be required for you. So that's why I've taken an overview of k nearest neighbor, and let's see, let's move forward. And we have a very important thing here, that is, we have to decide to some extent that whether I should use KNN or not. There is something. Naturally, you can go for k nearest neighbor because it is very simple, very simple. But the problem is that this determining this value of k, that means how many neighbors you will consider as a nearest neighbor. Based on that, you are deciding whether in which class you will put. That's a very crucial factor. So finding that value is very important. If you have anything wrong over there, your entire prediction will be wrong. But in the other side, definitely it's very flexible, because flexible to features and distance choice, because simple distance calculation is there, and the distance calculation function is the equation is very easy to implement, but it's very computationally high cost. Computationally high cost means it may take a lot of time because we need to compute the distance of each query instance of all training samples. So that means if you have a long training data, a very large amount of training data, for every iteration, calculating the Euclidean or Manhattan or Minkowski distance is going to take a lot of time, which will slow the algorithm. So that's a very big issue. Now, naturally, it's very easy to handle the multi-class cases. Multi-class case means if you have more than one class of data, but definitely storage is a very important issue over here. Anyway, but it can do well with practice, with enough representative data, but we have to understand that which particular distance function can be more useful. So you must need some trial and error maybe in future if you want to go for KNN, right? So this is the very overall idea of KNN, what exactly it is.